You're live. Welcome everyone to the e-poster session, and we will cover a number of topics in this session, including themes 3.2 laboratories, 3.5 data analysis, as well as 3.6 artificial intelligence and machine learning. And since we have a very dense list of poster presentations, I would like to start immediately with my Q&A moderator, Nicolas. Help poster to present with the floor.
Thank you. Good morning, good afternoon, good evening, wherever you are. I'd like to invite you to visit section 3.2 and look at our poster. In fact, look at all the posters there. They're all interesting. We have a poster on PTEs, proficiency test exercises, bringing certainty into uncertainty. As the title suggests, it's related to the uncertainty budget of reported results. Now, the radionuclide properties play an important role in treaty verification. On one hand, we have the contributing directly by analyzing suspicious samples, but also the supporting the IMS stations by analyzing QA samples that are shipped regularly to the laboratories. So we need a robust quality assurance program to ensure that the laboratories are performing well. So we organize these proficiency test exercises where an external provider sends certified reference samples to these laboratories. The evaluation includes, of course, an assessment of the uncertainty component, but within the acceptance range, there may still be some information where laboratories can improve. So we're looking at the zeta test distribution as an additional information. And so we have some interesting plots there. Go and have a look and enjoy. Thank you very much and enjoy the rest of the conference. And I hand back to my esteemed colleague. Thank you.
Thank you, Nicolas. I apologize, I forgot that we also covered topic 3.3 for remote sensing. And I would also like to mention that this session, as you can see from the variety of topics, covers really a very broad range of items that relate to the CTBT. I would like to continue with Shonyang Zhou next, and then afterwards with Peng Li. Shonyang, you have the floor.
Okay, I share my presentation.
Yes, please. We cannot see it yet. Are you able to share your screen, Shonyang?
Yeah, I tried. Yeah, I tried. It's okay. I am not sure how to play this one. I can't.
Just please go ahead and talk about your poster if we have technical difficulties sharing the screen.
Yeah, it's very difficult for me to share the screen. Yeah. That's what I can do.
Okay, we can come back to you later also after we have sorted out the...
Oh, later. Okay, thank you. Thank you.
Then I would like to continue with Peng Li. Peng, you have the floor.
Thank you. I met the same problem when I was dealing with the previous session. Okay, I have 4 presentations. 2 is regarding artificial intelligence. Can I do it all together? So the
Yes,
4
please.
presentations?
Yeah.
Okay, thank you. Can you see that?
Not yet.
Hello?
But something is loading.
Ask him to switch off his camera, Fission.
Okay. Can you maybe switch off the camera and only share the screen? It's coming now. Yes.
It's
Now
coming?
Yes. Now we can see it.
You can see it?
Yes.
Okay. So the first one is about commercial nanoset constellations application to multilateral arms control verification. This is something not really directly related to CTBTO, probably some other arms control verification regime. And we try to provide a solution based on nano satellite. From this picture, you will know the location, the spectrum of nano satellite would be some satellite which is very small, around 100 kilo. And its advantage will be light, small, smart, and cheap. And we can provide some kind of commercial platforms ranging from 10 kilos to 100 kilos. And we actually not only can provide remote sensing macro nano satellite platform, we can also provide communication macro and nano satellite. I can give you a number for the price. It could be something like 5 million for a small constellation. This picture will show some of the application scenarios. This is the first presentation. Second one is for commercial UAVs potential application. We provide this type of UAV. It's actually a manned helicopter. It is very mature and is suitable for application scenarios of offline inspection.
Maybe having a feedback loop on your audio.
Okay. The last 2 ones will be regarding artificial intelligence. The first one is actually for facial recognition based monitors. We can utilize some artificial algorithm to do the identification of different personnel. For example, we need to distinguish people from the inspection team and also people from the inspected state parties. So this can be used in that case. The last one is for artificial intelligence and also machine learning, the vision technology application to ISI scenario. This is something just providing some initial thought in this regard. We can put the AI and the machine learning technology as assistance to the OSI search logic, from data collection to data annotation to model training. And we can also see some of the advantages of AI, machine learning, and also disadvantages. We know that the trained model can mimic OSI expert thinking, more improved the inspection efficiency, reduce human error, but also it has some disadvantages. Probably this will cause some intrusiveness concerns. We want to illustrate some application scenarios. We applied the AI and the machine learning technology to the children autism spectrum disorder diagnosis. We cooperated with Chinese Beijing Children's Hospital, and we put forward this system solution. And now it's working for the diagnosis of children's autism spectrum disorder. Thank you.
Thank you very much for these very interesting presentations and posters, and I'm especially fascinated to see artificial intelligence and machine learning also be applied to OSI. I would like to continue with Nikolai Sidorov, and then next would be Amy Sandermeyer. Nick, you have the floor.
Hello, can you see me?
Yes, we can.
1 second, please. Can you see my presentation?
Yes, it's visible.
Okay. Hello, everyone. Hello, colleagues. My name is Nick Sidorov. I'm a research engineer from Vienna, from Moscow, and our team has developed the Russian monitoring system of radioactive xenon called MIX, and we have gained some experience in analysis radioactive beta gamma xenon spectra. And I would like to tell you a few words about our results in this area and key aspect of our poster. We present a new algorithm for analyzing beta gamma radioactive xenon spectra based on the maximum likelihood estimation, and there are some approaches to estimate the activity using beta gamma spectra. The most important and well-known of them are the net count calculation method, standard spectrum method, and machine learning and neural network. We looked in detail standard spectrum method and derivative from it, also called region of interest simultaneous fitting method. And standard spectrum method for radioactive estimation is inverse problem for linear task, and we've showed four possible solution to inverse problem, and we've identified the main characteristic of this estimator, and we consider the answer to question how to optimally create set of regions of interest, and we use only matrix approach to solve the problem, and matrix form of calculation MDA, MDC. We solve this problem in general way, and we also developed a software tool called XIMAT for analysis beta gamma spectra using a new algorithm, and all formulas are implemented in our software and our algorithm, and comparison between XIMAT and XICON show good agreement, and finally we think that simultaneous fitting method is superior to the NCC method in many respects and can be recommended as an alternative. We continue our research in this area, and thank you very much for your attention. Thank you very much.
I'm ready.
Convener, you
I
are
cannot hear. I'm sorry, I can't hear.
We are waiting for Amy to.
Hi. Yes, what would you like me to do? You have my presentation. Can you just play the slides that I uploaded?
Unfortunately, we cannot play any uploaded material in this session, but can you just highlight the key points of your e-poster verbally?
Okay, let me, yeah. Yes, okay. In that case, I will ask that people please go and play the video that I uploaded for my poster. Basically, what we are doing is applying waveform correlation. Let me see if I can share my presentation.
No video, please, only the slides. We had technical difficulties previously with playing videos over remote connections.
Okay,
If you can show the slides, that would be very appreciated.
okay.
Maybe we can see the slide.
Okay. So we use waveform correlation, and we're trying to reduce analyst workload by using template event metadata to more correctly apply detections. So the method that we're using starts by correlating templates with continuous incoming waveform data. And it's for nearby stations. So in our case, we're looking at applying this technique for mining blasts. We know there's a lot of repeating events. It should be possible to detect those repeating events with high confidence from nearby stations. But then the problem is you want to corroborate those detections. And so we use the template event metadata to find these potentially corroborating arrivals, because if an event was seen by a group of stations, then a similarly sized event, we are theorizing, should be seen by the same group of stations. So this is the start of the method. We take a detection. Here's an example for this one. This detection was from the LEB. The template was from the LEB origin 109-23214. Then we look at all of the other arrivals for that template event. We use those to create corroborating arrivals. So we make PN, LG templates for these corroborating arrivals. We use the reverse time method to set thresholds. And then we run detections. Now, what's interesting about using this approach is that when you look at what we're using for templates here, they're really not very good templates. You wouldn't necessarily add these templates to a library, but we can see that these templates have corroborating arrivals. They do detect things. And so when we then look at the combination of all of these corroborating arrivals, we can see here that the delta time tells us that it's likely that this is a repeating event because the time of the original differences in detections is very similar to what we're getting for the corroborating detections. And so we think that this approach can be used to find with high confidence repeating events in areas like mining regions where there's a lot of events that happen over and over again and have similar magnitude. And we hope to also take a look at applying this to aftershock identification. Thank you. Please go and look at the recorded video and the poster.
Sure.
Hello, Wolfgang. It's me or?
Yes, please go on.
Okay, thank you. Because you were muted before.
Oh.
Okay. Let me share my
sharing us.
Is this? Which one I'm share?
You're sharing your web browser where we see the conference platform.
Okay. Now?
Now you have stopped sharing.
Okay. Yeah, this one? It's okay?
We cannot see it yet. Can you share again your screen? Yes, now we can see it.
Okay.
This one.
Okay. Yeah. This my presentation is, yeah, the title is a little bit longer. Is there a potential for the future further enhancing of ADC spectrum analysis measurement method of CTBT radionuclide measurements after 25 years of progressive development? I prepared with my current colleagues and a few previous colleagues that made this many development and deployment in the past 25 years. This is an overview about the analysis method as ADC in past 25 years. So we'll show what we have developed and what's the potential problem and potential solutions to enhance the method. So the first method is the stack method for the gamma spectrum analysis of the particular sample. Yes, yeah. Actually, this single channel analyzer curve method is based on the Curie definition of the decision threshold, but actually it's a typical application of the Bayesian statistics. Yeah, we have another second method is the least square regression analysis for the gamma spectrum of lower gas. This least square fitting on the gamma peak regions and also the X-ray peak regions of the xenon isotopes. For the gamma spectrum with high resolution detectors like the Sparnax system. So there is some problem for this one. We don't have a very clear, concise definition for the decision threshold for the metastable xenon isotopes. Occasionally, we also observe some false positive or false negative detection of the metastable. There are some potential solution for this problem. Yeah. Next one is the NCC method for the beta gamma coordinate spectrum from a low gas system like the solar system. Yeah, we call it the net count calculation method. It's also called the Stockholm equation. It's finalized in the early of the 2000s. This has been a hot topic in the past few years, along with the new development of the next generation lower gas system, which all based on the beta gamma coordinate spectrum measurements. It doesn't matter if the high resolution for the Sparnax NG or other low resolution for the like Solar 3, Xenon International, and Mix. There are some challenges for this method. There is a high positive detection in the past few years, but I would say it's already fixed. Now, the key development along with the next generation is how to deal with this X-ray contribution and how to estimate the detect background. And then the effect is how to do the estimation of decision threshold and the other limits, characterization limits. Now we are in the implementation phase of the next generation system related analysis method.
So I don't want to be impolite, but we have only 2 minutes per poster, so I don't want to lose time.
Okay.
again for other presenters. Can you please proceed to the conclusions and key points?
Okay, that's the conclusion is that, yeah, most daily IMS spectrum has lower currents close to the background. So the decision threshold by the Curie definition might be underestimated, resulting in the false positive detection. So new enhancement and new development should be consistent with the recommendation from the ISO standard regarding the estimation of the measurement uncertainty and the characterization limits based on the Bayesian statistics. This is the first one. Can I show my second one together?
Please go ahead.
Okay. Okay. Stop show. And okay. So this is the Monte-Carlo method regarding the isotope ratio analysis. I prepared this one with my colleague Martin together. As I showed in the last slides, as we know, the isotope ratio can be used for the event screen. Also, it can also be used for the estimation of the nuclear explosion time. So the first issue is we need to calculate the value of isotope ratios. So in this presentation, we show a Monte-Carlo method how to do this estimation. If you see this equation, so actually the division algorithm of a random variable is a kind of the nonlinear model. So the value of the ratio are not, and the uncertainty are not depend only on the concentration values itself, but also related to the uncertainty and the covariance. So if you see this equation is still a complicated. If the concentration is not the measured concentration, we measure the activity in the sample or the peak counts in the spectrum. So it might be very complicated for the analytical analysis procedure. However, we can derive the distribution of the activity or the isotope ratios by the Monte-Carlo method, directly based on the input distribution of the peak counts or calibration data and other parameters. So here is the example. We use the Gaussian distribution of the concentration, and then we get the distribution of the ratios. It's not a Gaussian anymore, with the mean value of from estimated by this ratio with this distribution, and also the limits of the coverage interval. We can perform the event screen. With the distribution of the exploration time, we can estimate the mean value of the exploration time and also the limits of the coverage interval. So please come to the visit the e-poster for more detail. Thank you.
Thank you, Bokshe. I would like to proceed to try again see the poster of Shongyang Zhu. Is it working now for you, Shongyang?
Yeah, right. I try. I'm sorry. I'm sorry. This where to go? Yeah, right. I'm sorry. 这也玩不转嘛？是不是这怎么玩啊 ？I'm sorry. 窗口。对 Okay.
Yes,
Let's go.
Yes, we can see your slides.
Thank you. My name is Chongyang Zhou. I'm from Northwest Institute of Nuclear Technology, China. My topic is modification of OSI radio Xenon processing system. We have developed 3 generation OSI radio Xenon systems and take part in a lot of OSI activities such as FE14 and training inspectors. And this is the update, the modified Xenon 3 system Mark II. This is a sampling unit, and this is the purification unit. And here are some of the modifications: the traps from 2 to 4, and the measuring box from 2 to 4. And here's the temperature. I'm sorry. Here's the temperature. The temperature dropped for about 15 degrees, and the sampling volume is doubled from 2 cubic meters to 4 cubic meters. The merit of the example 3 is that daily throughput is 2 cubic meter 12, and 4 cubic meter for 6 or 12, and 8 cubic meter for 6. That's the daily throughput. And then 133 should be 0.7 millibecquerels for measured by becquerel. We will. This has made a great improvement. Thank you. I'm sorry this time. That's okay.
Take away his presentation.
Okay, very good. So I would like to continue with Michael Meyer. Michael, you have the floor, and next one up is CPD Salat Azimi.
Hello, everyone.
Oh, I'm sorry. We like to continue with Michael Meyer.
Recording.
You're next.
Hello, everyone. Let me share my screen. All right, so I have 3 posters, so I'm gonna just do them all at once. So the first one. So this first poster was on a technique to mitigate the effects of gain detector drifts through the use of larger regions of interest. So the activity concentration calculations rely on counts found in regions of interest. Should the gain of the detector drift between the measurement or between the measurements, the concentration values will be off. We explore the impact of these concentration values due to the drift, as well as using larger regions of interest to mitigate the impact. In order to do this, we simulated a detector drift by increasing and decreasing the channel to energy values. We also did a recalibration of the detector to determine the new efficiencies and the new interference terms associated with the larger regions of interest. And we applied these to actual sample measurements. So we see that if there's a gain drift in the beta or in the gamma detector, the xenon 135 is highly impacted, but with larger regions of interest, that impact is mitigated. And the same thing with the xenon 133, 133M, 131M. There's some slight variations, but with larger regions of interest, the variations become a little bit less impactful. How do these larger regions of interest affect the MDA and the MDC of the detector? And we see that for xenon 135, the larger regions of interest that I used increased the MDC or MDA by about 50%, but this can vary based on how large of a region of interest you vary with. I also looked at the gain drift of a beta detector, and obviously the 131M and the 133M were the most impacted. It's a little bit challenging to do larger regions of interest in the beta energy space, but this is due to the regions of interest for 131M and 133M being next to one another. All right, and if you have any more interest in this talk, please visit my poster. Thank you.
Thank you very much.
Now I will go on. Is it okay if I do the next two posters as well?
Yes, please go on. But
Okay.
please, we're running a bit short of time, so please keep it brief and
All right.
only highlight your main items.
Okay. So the next one is a method for calculating radon activity and radon rejection. Currently, the net count method does not have a method to look at, the activity of radon itself. And we came up with a method to actually do that by using the Bateman equations, as well as the values or some simulations from bismuth 214 and lead 214 to look at the fractional abundance of each one in region of interest 1. Using the activity concentration calculation, this can actually be used to look at the radon rejection of the system and see what sort of radon rejection is needed for its location. So if you know the radon in your area, you can actually use the activity of the radon to look at what the radon rejection of your system is. And if you have any more interest, please visit this poster. And the last poster is on performance monitoring of beta gamma detectors using QC data. Quality control measurement data is taken for all beta gamma detectors. And this is done mainly to look at the gain drift of the detector, but there's so much more information in this data, and PNNL has developed algorithms and software to monitor the state of the health of the detectors, as well as data acquisition system using the QC data. We look at the peak positions to look at the gain, but we also use this to look at control charts to make sure that over time the centroids positions do not drift. We also fit Gaussian equations to the 662 peak, as well as a rotated beta gamma, the Compton scatter peak, to look at the resolution of the detector over time. And we also make control charts with that. Additionally, per region of interest and per detector, you can look at the count rate and determine if there's a change in the efficiency of the detector. Again, if you have any more interest, please view the 2-minute video, as well as feel free to put questions on the poster. Thank you.
Thank you very much. I would like to invite CPT Sadat Asimi now, and next up would be Noriyuki Kushida.
Hello, everyone. Can you see my slide?
Yes, we can see it very well.
Okay. My name is Safida Azimi. I'm a PhD student from American University of Tehran. My poster is about analyzing radioxenon spectra with machine learning algorithms to predict activity concentration of each isotope. Detection of radioxenon isotopes releasing from underground nuclear explosions and calculating respective activity concentration is a very useful means to verify the nuclear nature of an explosion. In our work, by using the machine learning method, we aim to identify which radioxenon isotopes are present in a sample and predict their respective concentrations of each radioxenon isotopes. We test our approach with real experimental data collected from IMS station. Our method is distinct from defining ROIs or calculating counts. Our preliminary results show that our machine learning method is a promising approach to identify radioxenon isotopes in each spectrum and predict respective activity concentrations. Thank you for your attention, and please take a look at our poster.
Thank you very much for this presentation. I would like to invite Noriyuki Kushida now, and next up would be Reina Aurora. Noriyuki, floor.
Yep, I'm here and I'm going to share my screen.
Yes, please.
I hope you see my presentation slides.
Yes, we can see it very well.
Yeah, thank you. I'm Noriyuki Kushida. I'm here on behalf of Laurent Lubra because he is now chairing another session. And the title of our presentation is Simulation of Operational Results of NetVisa on a 3-month historical dataset. Probably some of you may know that NetVisa is a next-generation operational SHA event detector using the Bayesian approach. That means this is a kind of machine learning software. And it is still under development, but we set this in an operational environment, but partially. That means that the analysts still analyze the data, which is provided by Global Association. This is a conventional SHA event detector. But we also provide the events data, which are only found by NetVisa. So we are using the NetVisa in operation, but partially. So we learned that NetVisa shows a better performance than GA occasionally, but we only know the performance in the cell 3 mode, partial one. So we are performing the test of NetVisa in the full pipeline mode. That means we also take into account the retrieval of auxiliary data. And finally, we see that the testing results show a superior performance than GA. Let me little bit talk about the results of NetVisa. We compared the performance of NetVisa GA and as well as analysts using the ISC ground truth event. So here we prepared the data of August to October 2016. And in this period, we found almost 300 ISC ground truth events. And by matching the data, events, location, and time, we see that we have almost 200 the events analyzed by analysts, and also we found that 150 out of 300 ISC data are found by GA. At the same time, NetVisa found 250 events. So that means that with this, in this testing, NetVisa also surpasses analyst review. So this tendency also can be seen by comparing the overlap. That means the rate of the events which are found in analyzed by analysts and false alarms comparing to the analyst reviewed events. So this slide, the result agree with the performance in analyzed in detail. So we have some confidence that NetVisa really performs well than GA as well as analyst review. Thank you for your attention.
Thank you, Noriyuki. We'll continue with Reina Aurora, and next up would be Cyril Loachard. Reina Aurora.
Hello. Can you see my screen?
Yes, very well.
Okay. So I'm going to be talking about discrimination between earthquakes and explosions at teleseismic distances using deep learning. This discrimination is necessary for treaty monitoring so that natural events can be screened out by the International Data Center and national data centers can forge their own opinions. It can also be useful for building accurate seismic hazard maps. Current research on discrimination using waveforms or spectrograms is limited to events detected with 400 kilometers, which isn't applicable in countries with a sparse network of seismic sensors. This project investigates the use of deep learning on waveforms to discriminate between earthquakes and explosions detected at over 20 degrees or 2,000 kilometers away. We collected data from the ISC and IRIS and performed a high-pass filter on the waveforms to eliminate low-frequency noise, among other data processing steps. Our deep learning architecture consisted of a convolutional neural network for feature extraction, followed by LSTMs for sequential pattern recognition, and dense networks to produce the final prediction. The model achieved a promising test accuracy of about 90%, with an area under the receiver operating characteristic curve of 0.96. As you can see in the graphs, the accuracy is fairly consistent across different distances and magnitudes of events, despite the sparse training data in some cases. Our experiments show that deep learning is able to extend discrimination of earthquakes and explosions with waveforms to far greater distances with high accuracy. Thank you, and I encourage you to come to my poster session.
Thank you very much. Let's continue with Cyril Loachard, and then next would be Andreas Kohler.
Yes, of course. So I'm gonna share my screen. So can you see my presentation?
Not yet. We can see you very well, but your presentation is not yet on.
Sorry. So
yes, now it's coming.
okay, thank you. So hello, I'm a research intern at CEA France, and my topic was on filtering turbulent noise with interpretable neural networks. And our goal is here to predict, then filter time series of observables. And in fact, we make observation of a hidden dynamical system, which represents turbulence in the atmospheric boundary layer. And the goal of our work is to enhance the predictions of time series of interest like pressure or turbulent kinetic energy or air density. And our solution is to use Koopman operator theory, which guarantees that we can predict this time series. And we're going to use a neural network, a Koopman autoencoder, which allows us to represent the action of the Koopman operator. And we present here an application to the prediction of interest of time series of interest, like time derivative of pressure. And in fact, we see that we can interpret the behavior and the performance of the network thanks to Koopman operator theory. And our network is fully interpretable because, in fact, we try to make a spectral decomposition of our time series on some favorable features which are shown to be spined by Koopman eigenfunctions. And finally, the goal of our study is to determine the best architecture for our network. And there are two main hyperparameters. So one parameter which is an embedding dimension, named TED and the other named bottleneck, which is the maximal number of learnable Koopman eigenfunctions. And we see clearly that the performance of the network are interpretable fully thanks to Koopman operator theory. Thank you for your attention.
Thank you, Cyril. Let's continue with Andreas Kohler, and then next would be Li Yan.
Yeah, thank you. Hello, my name is Andreas Köhler from NORSA, and this is work done with my colleague Steffen Mehland. We explore the possibility of using unsupervised learning for identifying seismic event classes in signal-rich records, such as used for environmental monitoring. So the motivation behind this study is that manual identification of seismic events in long and signal-rich records is challenging and time-consuming. So power detectors such as STA, LTA provide a vast number of ungrouped events which cannot be screened one by one visually. Unsupervised learning is a good candidate to solve this issue, and there are a few recently published studies about that use deep learning for this task. Here we pursue a very similar approach. Our goal is to evaluate different methods, making use of open source codes and well-established machine learning models to not make it too sophisticated for the seismologists to apply these methods, and also to be applicable to different kind of data sets and tasks. So basically our workflow is to transform the three-component waveforms into spectrogram images and then use convolutional neural networks to extract useful features for finding clusters of similar images. And important, this feature extraction is making the spectrogram images invariant to time translation in time, because the signals might not be aligned in time necessarily. And then we visualize these features in 2 dimensions. And the last part is also crucial because that allows to actually evaluate if an obtained clustering actually makes sense given the domain knowledge available. We apply the methods to different data sets in environmental seismology. Here we show results for a seismic record from a glacier in Svalbard. And in this case, we found that different groups of ice quakes could be identified, as you see here on this figure. So in summary, we think that the combination of different methods which we explore in this study provides seismologists with a very useful toolbox to explore unknown records. And please have a look at the e-poster for more details and ask me if you want to know more about this approach. Thank you.
Thank you very much. So we have next up Li Yan and then Martin Kalinowski if he's joined.
You see my screen?
We can see your screen, yes.
Okay, I'm Li Jian from China NDC. It's my great honor to be here to introduce my poster. The title of my poster is Research on Local Seismic Events Detection Method based on the deep neural network. As we know, with the dramatic increase the number of seismic stations and the volume of historical data in the global earthquake monitoring network, the deep machine learning and the deep learning can be used in seismic data processing to improve the quality and the efficiency of the bulletins. So in this paper, we proposed an event detection method based on the deep neural network for multiple stations to detect local events. Our method first step is to use a multitask CNN to pick up the local phase. And first, the initial network model is trained using a large-scale data set from the Southern California seismic network, and then we use the transfer learning and the data enhancement methods to transfer the model to the small-scale data set of our target seismic network to achieve the detection the local P and S phase. The second step is to using the GAN and the STM joint network to identify the noise signal, because when we pick up the scientific phases, we still have some noise signals be detection. So we should to identify them and mask them to avoid these signals interfere with the follow-up processing. So the last step is we based on the principle that the local P and the S phase wave velocity ratios in the regional network are consistent. We established a local PS phases association method for the multiple stations to form the local events and to get the accurate time and locations. We use the actual data to test our method, and the results show that our method can can accurately pick up the local P and S phases, and then realize the reliable detection of the local events. So if you are interested in my work, you can see my poster for more details. Thank you.
Thank you very much. So this concludes our session on e-posters in this very, very wide area of topics. I would like to extend my appreciation for all the authors who presented their very interesting work. Unfortunately, we are running or have run out of time, and I would point your attention to that you can visit the posters on our conference platform, and through the chat function get directly into touch with the authors. We unfortunately don't have any time left for Q&A. So thank you very much for joining us, and all the best.
Muted.
Thank you.